Hey everyone, it's Dr. Calkins. Today, week 6, chapter 6, kind of tutorial over shape. I'll have a separate video to help you with both 5 and 6 when it comes to polarity and then polarity with shape. So with shape, we need to worry about, from our center atom, how many directions do we have? That's called steric number. Steric number is what I like to think of as directions from your center atom. So we have a choice of 4, or 3, or 2, and that's it. So a good example of 4 would be if we have carbon, we give it 4 electrons because it's in Roman numeral 4, hydrogen with 1 each, and then we connect the dots. Just like we did in our other video, we get methane. The problem is carbon isn't flat. If we were to build a model of carbon, we actually see this structure. So we have this kind of pyramid-like structure where we always have one kind of back, one kind of forward, and then 2 that are kind of in the plane. So if we draw that, it'd be almost like this one's coming forward. We show that as a dark wedge. This one's going backwards. That's kind of dotted dashed line. So it represents this idea of it's not a cross shape. The reason it's not a cross shape is because 180 and 90 degrees aren't the optimized angles for these kinds of atoms. What happens to be optimized is 109.5 from atom to atom to atom to top atom and so forth. So everybody in this atom is equally spaced apart, and that's what we want for our VSEPR theory kind of idea. VSEPR theory stands for valence shell electron pair repulsion theory, and that's what we're about to show you. This one doesn't really have much VSEPR going on because it doesn't have lone pairs to deal with. But we do have these 4 directions, and we have 2 ideas to worry about. One is called the electron pair geometry. So oftentimes we would say EPG for this, so EPG, and that's tetrahedral. Tetrahedral is because what we're seeing is what looks like this tetrahedron. It's kind of like a fancy pyramid. In reality, the molecular shape is what we want in the answer, and our molecular shape is still tetrahedral because lone pairs are the only thing that can change electron pair geometry and molecular shape ideas. So what are some other variations of 4? So we have this one of carbon, so I'll keep it kind of handy, hide its answer maybe. But if we move over in the periodic table briefly, we're going to see something very similar, and that is ammonia. Ammonia does not have a 4th bond, so it's going to be a different kind of tetrahedral-like shape. So it still looks basically the same, but because this lone pair up top is much bigger, it's going to make these atoms here squish down a little bit closer together. So whereas tetrahedral was a 109.5 degree angle, what we're going to see with ammonia, which is basically the same kind of structure, just has this gigantic lone pair. So here's the 1, 2, 3, 4. Here's the 1, 2, 3, 4 that gives it that steric number 4. It's still in that tetrahedral category, but because of its shape now is more steep, these would look more like what you see in Egypt. This is pyramidal, more like a pyramid. And you're going to lose about 2 degrees every time you add a lone pair to 107. So both of these are category of 4. This one just happens to be 4 bonds, 0 lone pairs. This is now 3 bonds, 1 lone pair, but still 4 either way. The only other one you have to worry about is water. And water has the same idea with hydrogens, but now 2 lone pairs that hate each other. So water is definitely not linear, as most students would draw it. So here's again methane. Here is ammonia. Very similar in their shape. Now here is oxygen. Notice when this happens, we have the same virtual kind of shape, but now we don't have 2 atoms up top. We don't have 1 atom up top. We have none. We have 2 lone pairs up top instead. That's going to squish these together even more. And when that happens, this would be the case for the camera angle. Here's your forward hydrogen. There's your reverse hydrogen underneath, as depicted by the wedge versus the dash. When this happens, you're still tetrahedral. So tetrahedral is the answer for all 3 categories as far as category goes, but what we care most about is the bent shape. because these two oxygens are bent close together. Again, lose 2 degrees every time that happens. So again, here's a summary of the 4. You can have 4 bonds, 3 bonds, 1 lone pair, or 2 and 2, but either way, you're going to have 4 total directions. Lone pairs and bonding pairs count as a direction or a steric number. So that was group 4. What about this group 3? So if we go to group 3, just go down and start fresh. What we're oftentimes going to see here is double bond. So if you have a double bond, maybe it's something like formaldehyde, CH2O, pretty common in the homework. You have a carbon with 4, you have hydrogens with 1, you draw it in symmetrically, oxygen with 2, you connect, you connect, you connect, connect. But notice you see that's double bond. That's a clear giveaway that 3 directions is going to have a double bond somewhere. Notice the 4 that we had earlier were all single bonds, and that remains to be the case. But if you have a double bond, you're going to be in this category. And when we make a molecule like that with a model kit, notice it looks kind of like a triangle. Right? It looks like a triangle if the double bond is there. It's triangular, yet it's also perfectly flat. So this side is flat, this side is flat. So as we rotate this molecule around, we notice that it's got 3 directions from that carbon atom in the middle. One just happens to be a double bond, that's irrelevant to this idea. But because it has a double bond and because it's flat on both sides, that tells us its name. So the electron pair geometry and the molecular shape are the same here because there's no lone pairs on carbon. They're all connected. So we call this trigonal because it shapes what looks like a triangle. So trigonal, but it's also flat, so it's called trigonal planar. Bond angle wise, we saw above that it was 2 degrees every lone pair, but here we basically have a circle cut 3 ways. So if you spin a donut in the parking lot with your car, that's a 360. Cut a 360 3 ways, you're going to get a 120 degree angle for trigonal planar. What might happen if we have a lone pair, like we did with nitrogen, or with 2 lone pairs with oxygen above? So what could happen there, it's going to look very similar. Let's say with ozone, this is a rule breaker. It's going to have a lone pair. I'll just go ahead and give the answer to save a little time. But it looks about the same. It still shapes what looks like a triangle. It's still going to be flat. Model kit wise, it's going to be fairly similar to what we saw a moment ago. So here's this side by side. Notice they're about the same. It's not perfect because these models aren't perfect, but now we're getting this squish underneath because this lone pair up top is so big. So these squish together, they actually bend together, and it too is called bent for its molecular shape. It's still in that trigonal planar category, so that category name is just to help us narrow down our choices, but it's bent, it loses about 2 degrees and 1/18. So here's again a summary of those kinds of things. They're both trigonal planar. You could do other examples like ethene is trigonal planar. There's just 2 trigonal planar atoms there. And then even like an SO3, still trigonal planar, still relatively the same shape, still got a double bond like all these others. So recognize mostly that if you're in the category of 3, you probably have a double bond somewhere, and that should help keep you from answering questions like it's tetrahedral or pyramidal, because those are single bond shapes only. The only thing left would be if you're in 2 directions only. So let's screw down for that one last time and think about it. If you only have 2 directions, you really just have a left and a right. No up and down, as in the case for 4. So when that happens, you could just be 2 atoms, like hydrogen and chlorine. Hydrochloric acid in a different chapter. When that happens, the shortest distance between 2 atoms is a straight line. Straight lines are going to be called linear for their electron pair geometry. And because there's no center atom, it's going to stay linear for the molecular shape. So the only time we see molecular shape changing as an answer is when there's a lone pair in the middle, and in this case the middle is a bond. Straight line is definitely 180 degrees, so there's that bond angle. You could also be 2 atoms but now a double bond. and that would be the case for, say, oxygen. When that happens, the shortest distance between two atoms is two straight lines instead of one, but it's still going to be linear, and it's still going to stay linear, and it's still going to have 180 degrees. The shortest distance between two could be maybe a triple bond. That's the case for nitrogen. So it's still going to share linear for the electron pair geometry and the shape and the bond angle, which is still now straight between two atoms. But what could happen is pretty rare, and that's two double bonds. Still linear, still cylindrical, just like the HCl. This would be carbon dioxide. It's got double bonds in two directions, left and right. So still linear, still stays linear, still 180 degree straight line angle. You could also be something like acetylene, which has a triple bond, and most importantly, this is the time we have central atoms. We have a triple bond linear here and a triple bond linear there. Acetylene, a good example because it has two atoms with that linear shape side by side. So a great way to recognize two is look for triple bonds. You can also look for things that have two atoms or things that have two double bonds, but most often linear is a triple bond. Here's another example with HCN, hydrogen cyanide. Notice it has a triple bond and it's still perfectly linear, just like the acetylene, just like the CO2, all straight lines, and just like those examples where we have only two atoms, those still linear, two atoms apart. So hopefully that gives you an idea of what to look for left to right when it comes to shape. Think about the center atom, think about how many groups, and then worry about lone pairs. If lone pairs happen, and they can for nitrogens and oxygens in particular, worry about what that means for shape with Vesper theory, and lose 2 degrees in your shape when that happens. So we'll catch you next time with some polarity and some of these shapes.